All right, so we can go ahead and get started. There's just a few of us here, so please just put in chat if there's any problems that you'd like to go over, either from the practice quiz or from the two previous homeworks, or any kind of material or concepts that you'd like to review, and then we can go through some of those problems. Okay, homework 6, problem 3, sure. We can go ahead and get started on that one. So let me get a blank slide. I don't quite have this one typed up. Okay. So for homework 6, problem 3, we have that you're kind of playing blackjack and you want to know the probability of getting dealt certain cards. So you're dealt one card face up and one card face down. And then we want to know the probability, and I'm imagining we can do part A of this. This was I think, kind of one of the more difficult problems in the homework, and one that quite a lot of people didn't quite get correct. And we can go through this. And so we want to find the probability that the bottom card is an ace or a king, and the top card is red. So how can we start this type of problem? We've got a probability of 2 events, and we want to know the probability that both of these events occur. The probability that the bottom card's an ace or king, and that the top card is red. So how could we start this problem? So not just find the probability of each event. So first we have to ask ourselves, are these events independent or dependent? What would you say? Just type in chat. Are these 2 events independent or dependent? Yeah, these events are dependent. Now, why is that? And this is a little bit tricky. There were a lot of people that solved this problem using the independent formula, and that's not correct. You can't do that for this question. But why are they dependent? Well, because if the bottom card that's dealt first is an ace or a king, then that changes the probability that the next card is red. Why? Because there are 2, red aces and 2 black aces. And same with kings. So if we happen to pick a red ace as our first card that was dealt to us, the probability that the next card is red changes. So that means that these 2 events are dependent on each other. So we need to use the formula for dependent events. And yeah, just like somebody typed in chat, yeah, we're picking without replacement. And whatever we get on the first pick, it's going to change the probability for the next pick. So they're dependent. So what we have is, let's call this event E1, that the bottom card's an ace or a king, and this event E2 if the top card's red. Then what we have is that the probability of E1 and E2, we have some formula for that. If we have dependent events, does someone want to say what this is equal to if events are dependent? Right, should know this. If we have 2 dependent events, there's 2 ways we can write this probability. Does someone want to give me one that might make the most sense here? Yeah, so Jordan, you're close. But there's one thing you're missing. So we would have the probability of E1 times the probability of E2 given E1. We need this extra probability times the event E1 out front. Alternatively, I mean, you could write it as the probability of E2 times the probability of E1 given E2. This is more complicated. The reason it's more complicated is because event E2 occurs second. We draw the bottom card first. The bottom card's dealt to us first. E2's the event that follows. And it's hard to find what this probability is just on its own, because there will only be 51 cards in the deck at that point. And it depends upon the first draw. So that will be much more difficult. Whereas if we do this one with E1 first, it's a little bit more straightforward. Okay, so what's the probability of event E1? Probability that the bottom card's an ace or king. Yeah, 8/52. Why is it 8/52? Well, remember that probability of events is just the number of events in the event space divided by the number in the sample space. Right, so how many possible cards could we draw? Well, there's 52 cards. How many are in the event space E1? Well, there's 8. There's 4 aces and 4 kings. So this is 8/52. And then we have the probability of E2 given E1. Does anybody know what's the formula that we can use for conditional probability? How do we find conditional probability for some general events? Yeah, so Jordan put in chat the probability of E2 and E1 divided by the probability of E2. That's correct. But we're trying to solve for the probability of E1 and E2. So that formula is not quite the one we're looking for. The formula, in fact, we're looking for is that the conditional probability of two events is just the number of events in the intersection divided by the number of events in E1. And now this is a little bit misleading. Some people get a little bit confused by this, but what this means and what this is described in the book is this is the number of total possible outcomes where we have both events E1 and E2, where we only care about E1. So kind of like the number of possibilities in the sample space, where we're looking at both events E1 and E2. So we need to look at how many ways can we have both event E1 and E2 happen. Well, we need to break this up into two cases. One where the first draw is red. So we have two cases. One where the first ace or king is red. And a second case where the ace or king is black, because that changes the probability that the top card would be red. So there's 4 ways in the red case that we pick an ace or king that's red. And there's 25 ways that we can pick the next card. That we could pick that the next card could be red, because one of them was already taken up here, so we've got 25. Then we've got 4 times 26 ways. And this covers the case where the first 2 cards are black. Then we've got 26 cards left over that are red. So we've got 4 times 26. And then we need to divide this by the total number of possibilities. Well, there are 4 options. Well, oops, there were 8 options for the first card. And then there's 51 options in total for the second card. This is the total number of possibilities that we have. And these are and the top part is the total number where events E2 and E1 both happen. And then if you work this out, so then we'll have like 4 times 25, or we'll end up with 4 times 51 over 52 times 51. You'll have 4 over 52, which will be 1 over 13. All right, so someone put in chat on my homework, I put 1 and 13 and acknowledged that the events were dependent, still got it marked wrong. You can put in a regrade request. It could have been possible as you have to use this formula. And this problem, there's several ways to get 1 over 13 as the answer and do it incorrectly. For example, if you solve this problem assuming that they're independent, you will also end up with 1 over 13, but that method is wrong. You just happen to get lucky in this instance if you assume that the events were independent. So depending on the formula, changes this. So you need to make sure you use this formula. Even if you said that they were dependent, but use like the independent formula, then that's where you might have still lost points. So somebody asked if I used the independent formula, but explained it why it worked in this case, even though they're dependent, would that be okay? I mean, I guess, but not really in this case, because there's the reason why they're dependent. The reason why the formula for independent and dependent works, you would have to like explain that the only reason this happens is because the probability that in ace or king is red is the same as the probability that the ace or king is not red. And because those two probabilities are the same, then you'll end up with some cancellation when you do when you use the you'll end up with some cancellation that happens in the independent formula, and that's the reason why this works is because the probability of these two events, the probability that the first draw is red or not red, are identical. But again, in this course, we haven't talked about why you would be able then to assume that the events are independent. So you would need to kind of have explained some sort of proof or something to really justify that, because that's not something we've discussed at all in class for this kind of weird case where these two happen. So you should just, if the events are dependent, just use the dependent formula. I mean, even if the events are independent, the dependent formula, like this general formula, always is true. So if you're not sure, this is generally just a good formula to fall back on, because regardless of whether they're independent or dependent, this formula holds true. And somebody asked, what's the formula for probability? Yeah, so the probability of E2 given E1 is the number of events in the intersection divided by the number of events in E1. But some students get a little bit confused. This is the notation that the book uses, and it's a little bit confusing. But what they mean here is the number of events where E1 happens, and we don't care about E2. But we still we just include all the possibilities. So that's why here we have 8 times 51. 8 is the number of ways that the first draw could have been an ace or king. And there were 51 ways for us to draw kind of the second card. So in this case, event E1 happens, and we don't know we don't really care whether or not the event E2 happens, whether or not the next card is red. We're just including all of the possibilities in the sample space where event E1 occurs. I hope that clears that up. Please let me know if that doesn't quite make sense, and I can try to explain it in a different way. Were there any other questions on this problem? I think part A was kind of the most difficult part for this question in problem 3, but whoever asked that, does this clear up the questions on this problem? Okay, I'll assume it does. So you can move on to another question. So if there's any other questions anybody wants to work on, we can go through some from the homework. If you have any questions there, as well, I have all the practice quiz problems that we can walk through if you want to kind of get a general view of all the concepts. I have some additional problems that you haven't seen before. Please just type in chat. Let me know what you'd like to see since you all are here. So if you have questions, please let me know what material you'd like to cover. So that way we can get them answered. Yeah, there's a precise definition for when two events are independent or dependent. Yeah, we certainly have a formal definition. And yeah, exactly what somebody just wrote in chat. So we know that two events are independent if the probability of A is the probability of A, given some event B. What this means, the way you can kind of interpret this is that regardless of whether or not you have some event B, that doesn't change the probability of A occurring, regardless of whether or not we know that event B occurred. So they're independent. But when you're coming up with a form, when you're looking at a problem, like these kind of real world problems, we know that events are independent if the outcome of one doesn't affect the outcome of other. So sometimes in real world problems, you can just figure it out on your own, and you have to kind of think about it logically to figure out whether or not the two events are independent or dependent, whether or not the outcome of one will affect the outcome of the other. Yeah, so somebody asked, can we go over telling if a list is an ordered list, unordered list, set, or permutation? Yeah, so somebody says question 1 of homework 5, we can sure do that. And after that, if you want some more practice, we can just quickly go through problem 1 of practice quiz 5 as well, because it gives some really quick fast problems that kind of review this material as well. Okay, so let's decide that decide whether these things are ordered lists, bags, sets, or permutations. So part A is the number of ways we roll a pair of dice. And we don't care which numbers on either dice. How do we count that? So I just want to shout out or type in chat.
When it says we don't care which number is on either die, what does that mean precisely?
It means that, say we have a die, this is like a top fever die, and we get a 1 and a 3. And let's call this maybe die D sub 1, and this is die D sub 2, but then I roll again. And this is die D2, or this is die D1. And this is die D2. In this problem, we're treating these are the same. So it means I don't care that in this case, these aren't different rolls. The fact that D2 rolled a 3, and in this case, D1 rolled a 3. I don't care because all I care about is that there was a 1 and 3 rolled. So I just care about the numbers, not what dice the numbers appeared on. Yeah, somebody says unordered list or bag. So yeah, this is a bag problem. We don't care about the ordering of the objects, right? We don't care about, you can kind of think about it as we don't care about the ordering. So if we roll a 1-3, that's the same as a 3-1. We don't care about the ordering that the objects appear in. We just care about the objects themselves. And that's by definition a bag. So the next part was the number of ways to select 5 pieces of chocolate. From a chocolate box, where all the chocolate in the chocolate box is different. So what would this be? So we're selecting some chocolate from a chocolate box. We're selecting 5 pieces from a group of unique items, right? Yeah, and somebody put it, yeah, that's a set. Why is it a set? Because all the chocolate in the chocolate box is different, so each one's unique. And we don't care about the order. So there's no repetition, and order doesn't matter. So we have a set. And then the number of ways runners can finish first, second, or third in a race. What would we have for that one? So any guesses for the runners? We've got a group of runners, and we want to know how many ways they can finish a race, whether they can finish first, second, or third. Yeah, so somebody said this one is a permutation. And yeah, the reason it's a permutation is order matters, but repetition's not allowed. You can't have the same runner finish both second and third place, but the order matters. We care about whether or not somebody finished first versus whether or not they finished second. So that's a permutation. Somebody else asks, why doesn't order matter for the chocolates? Because what we're asked in that problem is just counting the number of ways to select chocolate from a chocolate box. And so there's not like an implied ordering. I don't care whether or not I drew like kind of like a plain chocolate and then a caramel one that's like caramel filled versus whether or not I drew the caramel filled one or the plain chocolate one next. All I care about is what are the 5 pieces of chocolate that I grab at the end. So there's no ordering to that problem and no repetition allowed. And then so Alex asks, can we do 8A homework 5 and homework 6 number 5 at some point? Sure, I'll add that to a list of problems that we can take a look at. Okay, so let's look at this next one, the number of ways to split a class into 4 groups. How many ways are there, or how do we count this? Yeah, somebody put a set. Yeah. So why is it a set? Well, repetition's not allowed. If we're splitting the class into 4 groups, the student can't belong to multiple groups. And there's no ordering in the groups. We just care about which students go into which groups. So that's a set. The next we had the number of ways to rearrange the letters in the word theory. How do we count that? Yeah, permutation. Order matters because we're doing rearrangements, and repetition's not allowed. We can't repeat the same character multiple times because we're just rearranging the letters. So that's a permutation. And then the last one we had was the number of ways we would create a password with at least one upper case letter, one number, and one symbol. How do we got this? Yeah, ordered list. Order matters for passwords, right? It'd be kind of weird if you put a password into a website and the order of the characters didn't matter. So we've got the ordering matters, and you can certainly reuse characters. So repetitions are allowed. Any questions on this? If you'd like some more practice, we can go through the first question of the practice quiz that deals with this and does some kind of quick counting. If they're interested in going over that for some more review of these types of questions, or if not, we can move on to some of the problems that Alex suggested. So please let me know. So is there any more interest in going over similar problems? Like this, problem 1 of quiz 5 deals with a very similar thing about deciding how to count certain objects and then quickly count them. We can go over that if you'd all like some more practice on this. There were a few people who messed up some of these. So if you'd like some more practice, we can go over that. Please just type in chat. Let me know if that's something you'd like. If not, we can go through some of the problems that Alex suggested. Okay, we can start going through some of those. Okay. So I believe the first one, so homework 5, problem 8A. Let me pull that up. Oh, yes, this donut problem. We've got a bakery. And they sell 7 different kinds of donuts. And in part A, we want to know how many ways can the baker make a baker's dozen or a box of 13 donuts if each is to have at least one donut of each kind. So someone want to start out? How could we start kind of approaching this problem?
I made it into a problem that was similar to ones we've seen before, where we count the number of non-negative solutions to an equation.
Yeah,
But
that's
you have to do some
perfect.
processing up front to get it into that. Because if we have at least one of each kind, then we could assume that we're counting the number of additional donuts in each of our variables. So like x1 would be the number of plain donuts in addition to the one that must be in the box. So since we're having at least 7 donuts, then it should be equal to 13 minus 7, which was 6. So like x1 prime plus all the way up to x7 prime is equal to 6. And then you count the number of non-negative solutions to that.
That's perfect. So yeah, we take this problem and we convert it into a simpler, yeah. So this is a perfect strategy. So you take a problem and you notice, hey, can we rephrase this problem into something that we've seen before? And what we've seen a lot is we know how to solve equations like this and find the number of non-negative integer solutions. But here we have this additional constraint that all of them are greater than or equal to 1. And so yeah, like the idea that we've gone over in class is to just put that many donuts for each of those 7 types into the bag first, and then convert it to a problem about finding non-negative integer solutions. So we convert it into this equation. So we've got x1 prime plus x2 prime plus x7 prime, and that's equal to 13 minus 7, which is equal to 6. Right? Because the basic idea is we take each one of those 7 kinds of donuts and we kind of put them into our box. And now we've got 6 donuts left, and we want to find out the total number of ways that we can select the donuts of 7 type to get 6 donuts, or the number of non-negative integer solutions to this equation. And we know how to count that. So what's the formula here in this case? So we've got n is equal to 7. We've got 7 kinds of donuts. Then we've got r is equal to 6. We have 6 slots. So what's the general formula that we use for this type of problem?
C or n plus r minus 1 choose r. So in this case it would be 12 choose 6.
Yeah, so we've got C of 12 choose 6. And then what's that equal to? If we just apply the formula for choose, right, then this is just equal to 12 factorial over 6 factorial times 12 minus 6 factorial. And this is what we'll be looking for. You'll need to know how to apply these formulas and give answers somewhat like this. And then if you just want to check your answer, this turns out is equal to 924. So there's 924 ways that you can make this many boxes of donuts. And there was a question?
Yeah, can I propose an alternate but similar strategy and have you work through it real quick, or else tell me why it's bad strategy?
Sure, yeah.
So what if we just take the original equation, x1 through x7 equals 13 or whatever, and ask what are the positive integer solutions to this? That would force them all to be at least equal to 1. And there was this one pre-lecture video where they did a problem similar to that. And that's the approach I took, and I tried to like follow what they did in the video and ended up with a number that was off by an order of magnitude. And so I'm wondering if my calculations were wrong, or if that's a bad strategy in the first place, or if I followed the strategy wrong, or what.
Yeah, my guess is there's either some sort of mistake that occurs there, because that's actually the strategy that we did. And I'll kind of explain why. And the reason is rather than formula, because what we did is this first part really is about asking for positive solutions, positive integer solutions. And that's really what we're trying to solve. And what we did is we said, hey, if I wanted a positive integer solutions to this is difficult to count directly. But if I just subtract 1 from each of these, now I can just look at non-negative solutions to this. And that'll give you the exact same answer. So my guess is there must be something wrong in a calculation somewhere, because that really is the strategy that we did here.
Okay. Yeah, looking back on it, my work makes no sense. So I think I might have just brain farted.
You're good. No worries. Yeah, counting problems can be tricky sometimes. So any other questions on this part?
Yeah, so do we use C of R plus N minus 1? Is that when we want to allow repetitions? I mean, as opposed to just, I used to know this, but I forgot it.
Yeah, so this is a specific formula, and it's a formula that tells us how many like non-negative integer solutions there are to this equation. So yeah, we do allow repetition, but the ordering doesn't matter.
Yeah, Alec put it in
Yeah,
the
Alex.
chat.
Yes. Yeah. This is a combination, so we allow repetition, and ordering doesn't matter.
Okay, thanks.
Yeah, no problem. Yeah, just one of the formulas. I think it's in. These are all in like section 5.4. There's like lots of theorems that tell you how to count these things. I would certainly have those on my formula sheet. Those are the general ways to count lots of the problems that we deal with. So I'd recommend knowing those and having them on a formula sheet for the exam. Any other questions here? Not? Then we can move on to, looks like the next one. Homework 6, problem 5. Oh yes, this is that kind of long golfing problem. Alec, is there a part that people would like to do of that? There's 3 subparts. Oh yeah, and if somebody else wants to pick a question, please tell me.
It was all confusing for me, but I got A wrong specifically, but also happy to let someone else take a turn.
Okay, yeah, so we can take a look at homework 6, problem 5. If there's other problems that you want to look at, please just type them in chat. For the review, I want to make sure that your questions are answered. So if you have questions, or if you're just like, I don't have a specific problem, but I have a question about this type of material, please just let me know. So please just type those in chat, and we can go ahead and get started. Yeah, so we can take a look at problem 5A. I think that gives a good, it's very similar. Well, part B is nearly the exact same problem as part A is. And part C is just a similar problem as well. You just have to break down into cases. So yeah, we can take a look at part A. And this is something that's really good to look at too, because we have a lot of problems that deal with this type of kind of probability situation. So we have this golfer, and they get they're a really good golfer, so they get hole-in-ones with probability 1/3, par with probability 1/6, and anything else 1/2. Yeah, Alex said, yeah, hole-in-ones with higher probability than par. Yeah, they're a really good golfer. They get hole-in-ones all the time. And in this problem, we're kind of assuming that on this golf course, There is no par that's a hole in one. So for part A, we want to know the probability that in 5 holes, the golfer gets at least 2 hole-in-ones. So how do we find this probability that they get at least 2 hole-in-ones?
What I did was wrong, so I don't know.
Okay, and how about anybody else? Any ideas? What do we do in this type of problem?
You could just find the number that is like the complement and then subtract that from 1.
Sure, that's certainly. So the probability we get at least 2 hole-in-ones is 1 minus the probability that we get at most 1 hole-in-one. Now, how do we find this one?
Could we split it into exactly 0 and exactly 1?
Yeah, so the probability we get 1 hole-in-one plus the probability we get 0 hole-in-ones, right? Because these are distinct cases. So we can split them up like this. Now, what's the probability we get exactly 1 hole-in-one?
Can we use the Bernoulli formula thing, or does
Yeah, exactly. We've got a Bernoulli trial. Why is it a Bernoulli trial? Well, we've got 5 holes, and they're independent events. The outcome on the first hole does not change the outcome on the second hole, or the third hole, or the fourth hole, etc. If you have dependent events, you cannot use Bernoulli's formula. So this is always a good thing to check, that your events are independent. Otherwise, that strategy doesn't work. Yeah, so what would we have for the Bernoulli formula for this case with 1 hole-in-one?
It's n choose k times p to the k times 1 minus p to the n minus k, I think.
Yeah, so so we've got 1 hole-in-one, and we've got 5 slots, right? So we're choosing 1 of the 5 to be our hole-in-one. Hole-in-one has probability 1/3. We only want 1 of them. Then 1 minus the probability is 2/3. We've got that to the 4th, because there's 4 other slots. The probability 4th. And then for 0 heads, right, we're taking 5 and we're choosing nothing times 1/3 to the 0 times 2/3 to the 5th. And then if you work this out, you'll get that that's equal to 131 over 243. Is there any questions on this part?
Can we do B unless someone else wants something?
Well, B is the same. B will be nearly the exact same problem, except instead of whole at once, you're just going to do at least 2 parts. So the probability just changes. Instead of 1/3, you just replace that with 1/6. Instead of 2/3, you just replace that with 5/6. But then, I mean, you'll end up with a different probability once you do that.
Homework solutions are online, right?
The solutions to this are online?
Are they?
No, we don't post any solutions.
Oh, okay.
Yeah, none of the homework solutions are ever posted online for this class.
Yeah, could we do B and C? This.
Yeah, we can take a look at C, but B is the same. So where you just replace 1/3 with 1/6, the probability of par, and 2/3 with 5/6. And it's the exact same calculation.
Okay. Yeah, I got it wrong for some reason, but I got the first one right. I'll look at it later. That's okay.
Yeah, it could be, you could have like just typed it wrong in your calculator or something, did some weird error there. Yeah, but we can take a look at C. And then, yeah, Vista will get to that problem. We'll take a look at homework problem 7 next. So for C, what we're interested in now is we want to know the probability to get 3 whole and 1s, or that in 3 holes, excuse me, they get more pars than whole and 1s. So we need to break this up into cases, right? And kind of look at the probability that each possibility occurs. So what are the ways that this golfer could get more pars than hole in ones? Yeah, somebody says, yeah, they could get 3 pars. So maybe case 1 is they get 3 pars. They certainly have got more pars than hole in ones. So what's the probability that this happens? The probability we get 3 pars. Yeah, 1/6 to the third. There's a 1/6 chance that in each case, I mean, if you want to work it out like a Bernoulli trial, you've got C of like 3 choose 3 times 1/3 to the third, or 1/6 to the third, excuse me, and 5/6 to the 0. Yeah, and that covers that case. So what's another case? Yeah, so somebody says, yeah, so we could have 2 pars, and there's a couple of cases here. So we could have like maybe our case A is we get 2 pars, 1 hole in 1. And then maybe this case B is we get 2 pars and anything else. So the probability for 2 pars in this case, so this probability for 2 pars and 1 hole in 1, well, we've got 3 slots, we're choosing 2 to be pars. Pars happen with probability 1/6. And the hole in 1 has probability 1/3. Then in this case, we've got 2 pars, 1 anything else. We've got 2 slots. We're choosing 2 of them to be pars. That is occurs probability 1/6, and then anything else occurs with probability 1/2. And then we've got a final case. You could get 1 par. Yeah, 1 par and 2 something else. So in this case, probability for 1 par, we've got 3 slots. We're choosing 1 to be the par. Par occurs with probability 1/6. And the anything else occurs with probability 1/2, and we've got 2 of those. And then the values for each of these. So this one, you'll get 1/216. If we add up both of these, we get 5/72. And this will give us 1/8. And then we just sum those up. So you'll have 1/8 plus 1/216 plus 5/72. And that'll be 43/216. Which is approximately 0.1991. Now, one thing I always recommend doing, especially with these counting and probability problems, because it's really easy to make typos, mistakes when you're solving, or to apply an incorrect method. So I think always, at the end of these problems, you should always ask yourself, is this reasonable? So let's see, does a 20% chance seem reasonable? So we said that they wanted to get more pars than hole-in-ones. The probability that they got a par was 1/6. The probability that they got a hole-in-one is 1/3. So we should predict that this is an unlikely event to occur, right? If they get hole-in-ones 1/3 of the time, we would expect on average that they end up with more hole-in-ones than pars. So the probability that they get more pars than hole-in-ones should happen less frequently. And 20%, yeah, that seems reasonable. If we'd gotten a number, say 60%, now that might be a little bit of a red flag. That 60% of the time they get more pars than hole-in-ones, well, that seems crazy because the probability that they have a hole-in-one is more than a par. So that would make sense in that case. And then you'd want to look at your method and see where you went wrong. So are there any questions on this? No? Awesome. Okay. So now we can go to homework 6, question 7. Oh, yes. Okay. This problem. So yes, we've got this. Oh, am I out of slides? Out of spare slides. Let me just delete these. Okay. So in this problem 7, so we're basically randomly drawing this school committee. So we've got this 3-person committee. And we're randomly drawing them. And we have that the expect, and then if we say let be the number. Oh, this is homework 6, problem 7. The problem's a little bit long, so I don't want to write out the whole thing. So we're going to let X be the number of seniors on the committee. And we're given in the problem that the expectation of X is 2. And there are 10 juniors. So we're drawing this 3-person committee amongst seniors and juniors. We've got the expected number of seniors on the committee is 2, and there are 10 juniors, and we want to find the number of seniors. We just want to find the total number of seniors in this club that's drawing this committee. Okay, so does anyone have any ideas for how to solve this one?
What if we wrote out the expression for the expected value of x with a variable representing the number of seniors?
Yeah, that would work. That would work perfectly. So let's let maybe S be the number of seniors. Then the expectation is equal to 0 times the probability that x was 0 plus 1 times the probability that x is equal to 1 plus 2 times the probability that x is equals to 2 plus 3 times the probability that x is equal to 3. So the probability that x is equal to 1, right? What do we have for that? Well, we've got 3 slots. We're choosing one of them to be a senior. If there's one senior on the committee, we're taking from our S seniors, we're choosing one to be on the committee. And then there were 10 others, and there were 2 ways that we could have chose them, 10 juniors. And then we divide by the total number of possibilities. And there are S plus 10, choose 3 total people that we could have choose from. This is the number of people in the club, and we're selecting 3 of them. So this is the probability that x is equal to 1. Then we've got 2 times the probability that we can take 2 seniors here. So we take 2 from the seniors, 1 from the juniors. That's the total number of ways we could get 2 seniors on the committee. We divide by the sample space. F plus 10 choose 3. Then we could choose 3 seniors on the committee. And then we divide by the sample space. And yeah, we'd have something that looks like this. And then you'd end up with this, if you simplified it, you'd end up with this expression like, and then you'd plug in the value, the expected value. So we'd have 2 is equal to this formula. And then you'd eventually get that 2 is equal to 6 times and if you solve for S, that gives you that S is equal to 20. And yeah, that's a perfectly valid way to solve this problem. There's another way to solve this problem, and you kind of have to reframe your thinking about it. You can almost treat this. You can't directly treat this as a Bernoulli trial. Why? Because they're not independent. But what happens at the second draw depends on who was drawn on the first draw. But if you kind of treat it as a problem where we're drawing with 3 names directly and only look at the end, only look at names at the end, then you can still use the. Then what you can get is you can get the expected number is equal to 3, the number of people that we're choosing, times the number of seniors divided by S over 10, because that's kind of the probability in general that we draw a senior. And then if you solve for S here, we have that this part is equal to 2. And if you solve this, you'll also get that S is equal to 20. Yeah, I mean, if on like the test you had something like this, we do not expect you to solve an equation like this on the exam. I don't think you'll have a problem that would give you an expression such as that, but no, we would not expect you to simplify that on the exam. Yeah, if you have more questions, I mean, it's 3 right now, but we can keep going if you all have more questions. I am happy to continue working through problems. So if you have any more problems or material you'd like to cover, please just let me know and we can keep going through more. So somebody else have any questions? Can we expect on the quiz? I'm not sure. We haven't written the quiz yet. I mean, the length of the quiz, you can expect the amount of time will be the same as what we've done for previous quizzes. So yeah, even though the section covers 2 chapters, a lot of the material is really the same. Like we can test you on counting problems and probability problems in the exact same question, because lots of probability problems just ask you to count the number of ways to do something. So in just one question, we can actually test a lot of concepts. So no, they're not going to be twice as long as other quizzes and stuff. There will probably be more questions than on previous quizzes, because a lot of counting problems don't take that long. Some of them are pretty quick to do. But the overall length, the amount of time the exam should be equivalent to what you've seen in this class for the 4 previous quizzes. So I hope that somewhat helps. So between counting and probability, one would probably want to be more confident in count. Yes, if you had to pick, you'd probably because counting just generally leads to a lot of probability, right? Yeah, like for this example, we are finding the probability that x is equal to 1. That's just a counting problem. You're counting the number of ways that you could have 1 senior on the committee and dividing by the total. I mean, I'll study both. They're both heavily related to each other, these probability and counting problems, and they really deal a lot with the same material. Well, yeah, if there's no other questions then yeah, we can call it a day then. I'll still have office hours until 4. If you want any one-on-one time for any questions on either homework 7 or just some other questions you had,